All right, just a second, and I'll bring it up on the screen for you guys. Confirm that you're seeing the screen. Does it look okay?
It's up.
Oh, great. So this webinar today is covering a broad range of topics that researchers in suicide deal with regularly. So I think that many of us are very aware of analytic approaches for and the common biases of working with rare outcomes. How we may not think about it on an everyday basis. And so I just wanted to bring together some of the main challenges that are that we face with when working with a rare outcome such as suicide. I put this webinar idea together. All of the various topics that could be covered, all of which are very important. I think that it'd be a couple pros and cons came out of that. One being that there's a lot of important things to talk about. However, an overview of just a handful of them means that it's not really going into depth from a methodological standpoint on any one of them, because it would take probably a webinar in itself for each of them, really, to get it from a statistical standpoint. And knowing that many on these calls are also clinicians, I don't want to give too kind of way statistical understanding of something that could end up being more confusing than not. So the goal for this presentation is more to kind of bring to light some of the common challenges that we face and propose important ideas that researchers and clinicians should be thinking about and when these problems come up. Propose a couple alternative approaches or solutions, but not get into the nitty-gritty of the statistics of those solutions. At least, some of them are going to be topics of future webinars. I'll be happy to talk with you further about. But today it's going to be more of an overview perspective. And to start with, I just want to talk about what constitutes our outcome. We talk about suicide. We don't talk about it as a rare disease in this country. It is the 10th leading cause of death and a major public health problem. First, I'll talk about why, why is that? How is it a rare outcome when it's a major public health problem and a leading cause of death in the United States? And then I'm going to present these are the five common challenges of working for outcomes that I'm going to present today. There are certainly many other challenges, and there are certainly many other solutions, both from a statistical standpoint and a study design standpoint, that I'm going to present here today. These are just some ideas and an overview of those ideas, as I said. Rare outcome. In the United States, a disease or disorder is considered rare, according to the NIH, if it affects fewer than 200,000 people in the United States. Of course, suicide is considered a disease. It's a cause of death. It doesn't make it onto this rare disease list. That makes sense. It's basically just definition. Different, and it's the 10th leading cause of death. But I know there's only about 41,000 suicides per year. Although the suicide rate is high and increasing, that means that from a count perspective, this is pretty rare. If we're dealing with rare diseases, this would definitely fall in there, and we're likely to come across and many of the problems that occur when studying rare diseases due to the fact that there is simply a low number of individuals with our outcome of interest, suicide. And those numbers drop considerably further and often very fast when we're looking at subpopulations of interest. Those subpopulations may be at high risk, but their counts are going to be low. And I'll get into that a little bit further in a moment. That's kind of that rare disease definition. From a statistical standpoint, what counts as a rare outcome? The definition that's often cited over and over again is incredibly vague, kind of comically in a way. King in 2001 in an article said, it's a binary dependent variable characterized by dozens to thousands of times fewer non-events. So it's basically the event is considered less common than not having the event. In this case, dying by suicide is not dying by suicide, but it may be dozens to thousands times fewer, according to this, kind of generic definition. And it often really comes down to the counts that you're working with in a given study. A kind of statistical guidance, some of which I'll get into further specific examples and challenges we face. Consider rates to be unreliable when they're based on fewer than 20 cases. So when you're working with less than 20, you really can't get a good sense of you have less than 20 individuals with your outcome of interest. You can't get a very good sense of rates, and that can be a very challenging problem when you want to compare between different populations to determine who's at high risk, to see how rates change over time within and across populations. So whenever you're kind of below that 20 count, you tend to have a lot of arching challenges to face in terms of even understanding the magnitude of risk within a population. And from a statistical standpoint, there's varying sample size requirements for specific statistical methods. This is really the whole reason we do power and sample size estimations. We're planning a study, and it's really based on the methods that you want to employ in order to answer your question of interest. An example of one of these is a simple rule of thumb, where we often say, and I'm going to talk about this later and whether it really is the case or not, but a general one that many people know and are taught in the FB courses is that you have to have 10 outcomes in your model for every covariate you put in. So if you have a study and you have sides in that study, you're going to be able to adjust for much in a multivariate model simply because you have a few number of outcomes, even if you're not trying to compute, say, but looking at ratios and other things that are estimated by those methods. It really just depends what you want to do, what your statistical analysis is. But we come into the realm of a rare event that causes problems from an analytic standpoint when we're working with suicide. Said this often becomes a problem because suicide is a very heterogeneous problem in many ways. We have lots of different populations who are at high risk, and they can be very different from one another, and their risk factors for suicide and effective treatment or preventive factors that we want to enhance differ between these high-risk populations. The 20th National Strategy for Suicide Prevention names the following high-risk groups here: American Indians, Alaskan Natives, individuals bereaved by suicide, individuals who have attempted suicide, LGBT populations, members of the armed services and veterans, midlife, and older men. These are very kind of diverse high-risk subgroups. They're risk because the rates for suicide are higher than average in these groups, but the magnitude in terms of the data we have to work with, and when we run into these kind of unevent problems, has to do both with risk and population size. So here's kind of a classic example discussed in the national strategy, actually, is that white men who are 75 years of age and older have the highest rates. Most deaths from suicide occur among white men in midlife, and that's because that group makes up a larger part of the population. So the rates are lower, and if your actual population that you're looking at is larger, you're less likely possibly to run into views of a rare event, because sometimes it's the count that matters, not the rate, the actual number of suicides. And many of the populations, those listed here and others that are at high risk for suicide, are relatively small in size. Despite the elevated risk, the number of events can be quite small, and it really compounds this rare event problems that we run into, or challenges. Here's another example of that. With my work, I work for the Department of Veterans Affairs at the 2019 Rocky Mountain Myrick for Suicide Prevention. I'm an epidemiologist, so I work primarily in risk factors among our veteran population. I know that approximately 7,000 veterans die by suicide each year, so that's a much smaller number. And of course, we only have we often are doing research among veterans who are using VHA services. Only about 30% of veterans use VHA services. So that right there is going to cut our numbers considerably. When we want to look at key subgroups, even just looking by gender or looking within key patient populations that accounts of suicide over certain time periods can drop very quickly. This is the VA's 2016 suicide data report that came out in August, talking about figures a bit out of context. In the report, it talks about really understanding where to focus our efforts, because of the problem of the suicide problem among veterans is a combination of the size of our population subgroups within the veteran population, and then the suicide rate. And this is showing age specifically. So it's showing how suicide rates vary by age, but then population varies by age, and this is for males specifically. And it just kind of points out this key point I'm trying to make. With a simple one but important one, that sometimes high risk means low numbers, even though it's much higher risk. For example, here for the older men, or younger men, I'm sorry, on younger male veterans, you have the rate line there in blue, and the rates over on your right-hand side. You have considerably higher suicide rates of about 85 per 100,000 population of male veterans in the 18 to 29-year-old age group is small. You see that that's not necessarily where the burden of suicide falls in terms of the number of deaths by suicide that we see. And thus, we really understand from a research standpoint what's going on with that high-risk population. That's often a question now that maybe age, maybe other high-risk populations, but some populations are small, the counts drop drastically, and make it a challenge to understand risk among very important subpopulations where risk is high. And this is, and an example of that when we go even further, we have a much smaller proportion of females in our veteran population than males. And this is all veterans. This is not even just veterans using VA services. We see basically elevated risks among, as an example, our younger women veterans, very, very, very small. This population that we're particularly concerned about and interested in learning more about, and making sure that we have or that we developed intervention strategies that work for our female veterans whose suicide rates are elevated considerably compared to their civilian peers, whose suicide rates are rising rapidly. Then at the same time, our counts are very low. And again, these are all veterans. We have, the ability to do studies within the VHA that are considerably lower, again, with only about 30% of our veterans using the VHA. And here we have a count of around 50 for our 18 to 29-year-old females per year. So they drop drastically, and it's really this magnitude and this problem of rare events depends a lot on, what your question is and what your subpopulation is. So definitely a rare event, more so in some subpopulations than others, and then in the subpopulations where it's maybe not rare because the rate is elevated, rare event problems because the counts are very small. And so I kind of alluded to before, a basic but very important challenge that we face is computing and comparing rare event rates. It's kind of just a general discussion of computing rates. Again, not going to get into in a very detailed way during this talk, but I'll surely be happy to answer questions if you had any. But computing rates, it's guessing everyone probably has a sense. Suicide, we're often using annual mortality rate. A simple, crude annual mortality rate is essentially the number of deaths observed divided by the population at risk. And we get the population at risk using persons, which is basically the count of individuals we generally estimate with a mid-year estimate based on census data, or if you're looking at a patient population, your healthcare system data, things that just an estimate that we have for the number of individuals at risk, which means they had the potential by suicide. So according subgroup, your denominator, your population at risk has to match that subgroup you're looking at. Or you can compute person time, which is an estimate of person, or it's based on precise count, which looks at the exact amount of risk time that each person contributes. So if they die of a competing cause or the cause of death itself, their risk time for that year stops, and it gives you a more accurate way to calculate mortality rate. In the end, the mortality rate or annual mortality rate that you calculate is essentially comparable. And so if events is small, is that rates can become both unreliable and unstable. Stability is really also the accuracy or precision. And I don't want to get into too much in the way of statistics, but really to have this as a problem, we have to at least touch on it. Error is, of course, when we, from an estimation standpoint, when we estimate a rate or any estimate, we have basically a probability of error around that estimate. Your standard error is a way to quantify how wide that error is. It's basically what goes into our confidence intervals, so that we can say, our best or average estimate is X, and the confidence interval gives a range of, we're 95% confident that the true value is between value and another value, and your actual estimate is going to lay in there. So the wider those confidence intervals get, that reliable, accurate, or precise rate. Essentially, if it's very wide, your estimate is an estimate, but we don't really know if the true value is at one end of the confidence interval or the other. And when the confidence interval gets wide, really assume that the average estimate that you make is reliable. Very important is the best way to put it. The way we quantify that is something called relative standard error, and relative standard error is just the standard error as a percentage of the measure itself, in this case, the rate. So a relative standard error of 50% means that the standard error is half the size of the rate. So that gives you a very wide confidence in other words, confidence interval in other words. Here how it's calculated, really don't need to go through that in detail. Essentially what we see, I didn't mean to put forward, what we see when we map out the relative standard error, and there's not map out, you graph out the relative standard error, which you see at the bottom here, that when you have a number of cases or number of deaths below 20, your error jumps drastically and quickly. Around 16, if you have counts of less than 16, your relative standard error is 25%, and the 95% confidence interval is at least as large as the rate itself. So you could have a rate of per 100,000, and your count would be as wide as 0 to 60. It wouldn't. That doesn't really mean much. And generally, when we generally do not report rates, or they're suppressed when the count is less than 16. The National Cancer Institute does use that 16. Many other organizations actually set the cutoff more strictly at less than 20. Department, like the New York State Department of Health, other departments of health, for health statistics, they set the cutoff at 20. Another issue. So the first issue had to do with what is the actual rate, and when we have low numbers, it's hard to know what the true rate is. Stability has to do with the fact that when there's only a few cases, it's also impossible to distinguish random fluctuation from true change. And so that random fluctuation is important when we generally don't just want to know a rate at one point in time or in one population. We want to be able to compare. We want to compare rates across groups, and we want to compare rates over time to look at trends. Numbers and yours aren't stable because they can be influenced rapidly by a small change in the count or number of deaths. Then you don't know if the change you see over time or the differences you see across groups are true differences or if they're random fluctuation. And that issue can be seen here on this graph or table, just very briefly. With a quick thing that when you, and I just generated this quickly, a very small counts or number of deaths by suicide of, say, 10, and this could be different populations or it could be different years. Let's just say it's the same population, female veterans who use VHA services, and it'd have to be some other subgroup as well because there's more than that. But anyway, it's a smaller subpopulation. You want to see how their rates change over time for looking at evaluating programs to see how treatment effects are working and just general trends over time as population characteristics change. In this case, when you have, say in 2013, you had 10 deaths, and then in 2014, you had 12 other parameters here. The percent difference in rates, the rates don't look very different. We have 1 per 10,000 or 1.2 per 10,000. And again, this isn't really necessarily suicide. It's just an example of rare events. But the difference, the percent difference between those two rates is pretty high. It's 18%. However, those the difference of 2 there could be due to random fluctuation, as I said. It could be due to the time frame you set for the study. So some very generic. It could be a calendar year, but suicide on one day or the other day, or one day prior to the cutoff, December 31st or January 1st. Those are an arbitrary cutoff, even though it's a calendar year. It's a true cutoff, but when the event actually occurs, obviously puts it in one or the other. And I wouldn't necessarily call that random fluctuation, but it just shows that the meaningful change in rate is harder to observe when it can be put in one bin versus the other. And that bin could be time. It could be just classification of cause of death, especially when we're talking about suicide. Accident overdose is a very common one that's discussed often, whether the overdose is accidental or intentional. Sometimes hard to tell and classified as a suicide or not when you have very small numbers can quickly change the rate and contribute to this. It's not necessarily random. There's a reason for it, but it's fluctuation that isn't a true difference in rates. And then, of course, just normal random fluctuation. And just a bit higher at 50 and 52 here as a comparable example, that percent difference is only 4%. We probably wouldn't, when you're looking across time, it would really depend on the overall trend, but you can see how rapidly, if you looked for many years, if you saw large fluctuations, it'd be hard to tell if there's an actual increase in that fluctuation or if all you're seeing are large random fluctuations. And that's the issue of stability. This is particularly important sometimes because when you're calculating rates for the full population, they're not estimates. And the first thing I was talking about, accuracy or precision, is not really the issue at hand. It's not about whether rates are reliable, but whether they're stable. So if you have all veterans or all whatever population you're looking at, you have the rate you have. It's a population rate, an estimate by any means. However, you still are going to have challenges with this stability, volatility of the rate, and it makes comparison between groups and across time challenging. This challenge of small numbers when computing and comparing rates only gets compounded, again, when we're comparing rates. This is because we have when you have those unreliable estimates, they have high standard errors. When you base another estimate on an estimate with a high standard of error, the comparison estimate has an even higher standard of error that just sort of compounds on itself. That's kind of a statistical principle. You also be more likely to encounter an issue of small numbers because when you're comparing groups, you need to adjust for other factors. And when we compare rates, for example, we at least often age adjust. And because for suicide in particular, and this is often the case for many other diseases that are rare and outcomes, but the rate of suicide differs considerably by age group. And if you have two populations whose age distributions are very different, if you just compared their crude rates, it'd be hard to know if the difference in rates that you see is due to the fact one population is very young and one population is very old, or to have to do with other differences that we're trying to identify in the population. Say for veteran civilians, we're trying to understand if military service or other factors that influence one's choice to join the military are related to their suicide risk. But there's also a large difference in the distribution of our veteran population and the age distribution of our civilian population. So of looking at veteran suicide, we certainly cannot just compare veterans to civilians without taking into account the difference in age distributed to populations. Age compositions change over time, also a problem we run into for veterans and other important populations as well. Our veteran population ages. Right now it's much younger because of the influx of OES veterans, things like that. So you constantly have a population where your age distribution is changing. And you have to take that into account. But the ways that we do that when we age standardized rates put down our population further into other subpopulations. Then we have the issue of small numbers in those specific age groups of our subpopulation, and it makes comparing rates very. So, or approaches, I really say, to this problem are somewhat. There's not always, and this is kind of the case for a lot of the things I'm going to discuss today, there's not always something you can do. Sometimes the most important thing is to be aware of the problem and make sure you're presenting your results in an appropriate way. There are some things we can do, and they're relatively simple. We can condense our data to ensure that we have adequate numbers for reliable and stable rates. When we're doing mortality rates, this can often be done by grouping multiple years. For example, you can provide 5-year average annual rates. So you group your data up for 5 years, you calculate that rate, and then you divide 5 and you get the average annual rate. And the more stable way to do, because you're not as influenced by those random fluctuations over time. Issue is not if you're able to group up to numbers greater than 20, for example. And if your subgroup of interest happens to be geographic, you have to group up your geographic regions until you have a large enough population. And you group similar subpopulations of interest, or really what that comes down to is often resisting stratifying. Again, for example, I work with veterans always interested in gender stratification, and really always an interest in suicide work, but it's not always feasible, say, in the veteran population, because for our women, that's such a smaller subpopulation. If we don't have the numbers that we need in certain studies for rates, when we have the population of all veterans, we're able to, but we may not be able to age adjust in this next kind of bullet here, fine-tuned as we could for males. So you really just have to, when stratification is appropriate and feasible, and then you have further considerations to make in terms of adjustment, for example. And because it is very important to be able to compare rates, oftentimes the comparison of rates is what you're after. Even if you can't calculate the rate itself, you want to understand if one population is at elevated risk compared to another. And the recommended way to do this when you have low numbers is with a standardized mortality ratio rather than an age-adjusted relative risk. And again, not getting into the statistics of it, something to remind people of in terms of an appropriate method. When you use methods, the standardized mortality ratio that you get does approximate the relative risk or the age-adjusted relative risk. What's possible is that you have whatever your larger comparison population is, you use the age-specific rate, apply them to your study population of interest, that is likely your smaller population with lower count, and you generate an expected number of events that you would see in your study population if your study population had the same rate as your control population. And then you're able to see if you've observed fewer or more events than expected, and that estimate, you're able to give you an estimate of the relative risk. Safer approach, because you're actually not using the rate from your small study population, which may be unstable. You're using a more stable rate from a larger population. So if you're kind of working out that issue of those issues of instability and precision using this method. And then, not necessarily a solution, but just that we need to be aware of how we present our findings. This is an example from CDC where you can go in for any underlying cause of death and look at crude rates. And you can also, in this example, you can request age-adjusted rates. You can request for certain years. changes over time. It's national data. This is not an estimate. It's the population. However, and the extreme examples, but I just wanted to demonstrate how they display results. And you can see here that using ages, but there's many other ways you could come up with small numbers. Suicide, they at least very clearly state that the rate, they don't even give the rate, although you could, the funny thing is you can easily calculate it from what you have there. It's the number of deaths divided by the population, and then you would multiply by 100,000 if you wanted it per 100,000. You can easily calculate that. They don't suppress the count, but they do unless you ask them not to. But state very clearly that the rate is unreliable, and they give just a confidence interval. Now that confidence interval seems pretty tight. That's because the rate is very low because the population is so large and the count is low. But there can be cases where your count is low, but you're working with a small subpopulation, and then the estimate itself would be higher, and the confidence interval would be wider. So not the best example in some ways, but more of a display here of output and the way we want to be careful displaying our results when we have our event rate. A lot of discussion over a relatively simple topic. I'll try to speed up here, but that last topic is one that I work a lot because it seems very simple, but when we're trying to establish risk and age of risk over time, there can be a considerable amount of debate surrounding rare event rates. Surprisingly, a lot of consideration goes into it. Challenge 2 is identifying individuals at high risk, and this is really for suicide or imaging. This is the topic that gets a lot of attention in terms of suicide risk assessment. It's often described as the classic we need to find a needle in the haystack. Again, of that kind of generic but classic definition of a rare event, thousands of times fewer events than non-events. So how do you find those individuals who are going to have an event before they have one? The number that are going to have an event is so small compared to a large pool of those who will not have an event. The U.S. Preventive Services Task Force, as of 2004, did not even recommend screening for suicide because there was a lack of evidence showing accuracy and effectiveness. That's not, many clinical recommendations surely recommend that we screen for suicide, and there's a lot of recent discussion about improvements in suicide screening and the importance of doing it. I am no way advocating that we don't, just stating that because of the challenge, it's very hard to recommend a standard screening protocol because it's very difficult to create a screening tool that can identify those at risk with a high predictive value. Selling, as I said, one example being the COLIA scale. But even tools that exist for the most part, they focus on collecting information on kind of classic risk factors: previous suicidal behavior, current suicidal thoughts, ideation, risk factors, access to lethal means, those traditional risk factors for suicide. That even when you're looking at the highest risk populations, such as individuals with a non-fatal suicide attempts, the majority are not going to die by suicide. And with a small number of true positives, you have a low positive predictive value. Exactly what I'm talking about here, kind of from a statistic standpoint. Values that we think about when we talk about screening tools are sensitivity, specificity, positive predictive value, and negative predictive value. Sensitivity is, using tools have the proportion who die by suicide was the proportion who are identified by the assessment tool at high risk. It's the proportion of people who do not die by suicide who were not identified as high risk. You are your true positive, so there are the portion of those who we do identify who later die, and the predictive value is your true negative, portion of those not identified as high risk who do not die by suicide. So this is what resources often, even if we have a highly, pretty sensitive and specific assessment tool, positive value is a very important measure in that if we're going to put a lot of resources to assist individuals who screen positive. If there's a low predictive value, then we're into a large group of individuals who won't die by suicide. Not arguing whether that is or is not from an ethical standpoint what we should do, but that's kind of the problem because of their event. To set into perspective a little bit, I did set our comparables for suicide. Given the audience here, you can see that if you have rates per 100,000, with 30 being kind of an average rate, and then here we have much higher rates for certain high-risk populations, whether those be clinical populations or other demographic subgroups. Just for examples here, you see that the positive predictive value for an assessment tool has a sensitivity of 67%, a specificity of 76%. I use those because that's what's estimated for the Columbia scale. The first at the colored line at the bottom here is a positive predictive value in that scenario. It's real low. It's real low. Even if you had an elevated suicide rate in a clinical population, say of 300 per 100,000, or even 3,000 per 100,000 in a very high-risk clinical population, even with a pretty good assessment tool, you only have a positive predictive value of 8% of those 3,000 per 100,000 risk, and means that only 8% of those who screen positive will go on to die by suicide. So a large number of those who you're going to treat based on the positive screen are not truly at risk, in other words. Even if you have an incredible screening tool at the bottom, if you just propose there's a screening tool with 95% sensitivity, 99% specificity, those numbers surely jump. But in situations where we have most of our risk level for suicide out of 30 per 100,000, or maybe moderately elevated clinical, not moderately, considerably, but many populations where this is true, 300 per 100,000, you have still relatively low positive predictive values. So this is just kind of the situation. This is why there's a lot of talk about we need better screening tools for suicide, but when it comes down to it from a statistical standpoint, with the rare event we're working with, and this is really not unexpected at all. Solution approaches, again, it's not really, maybe in some ways, methodological one, and I'll go over one idea for that, but in a lot of ways, it just comes down to, what's most important here. Do we need to focus, often, and we need to focus on sensitivity and less on this positive predictive value. And that just basically means we accept the high false positive rate and positive predictive value because the outcome is serious and warrants our resource expenditures. And that's what is done and needs to be done. We can't not identify individuals at high risk. We seek to develop highly sensitive and specific screening tools, as I kind of showed on the other end. Obviously, the better the screening tool, the better the positive predictive value we get. That's true, but we are bounded by the fact that it's a rare outcome. However, there's, from a methodological standpoint, there's a need to go beyond traditional risk factors. An approach that's becoming more popular, it has been used in the VA or is being used, and also within Army STARS is another example, is predictive analytics efforts, machine learning, big data, analytics often called, but essentially this is the use of statistical risk models that can large number of variables. Oftentimes those variables are collinear, but the methods are statistically advanced to be able to account for that. And the goal there is to generate a risk score and to stratify risk rather than simply identifying those who are or are not at high risk based on a simple screen tool. And models can take into account clinical indicators, non-clinical indicators. Machine learning techniques can use any information on an individual that we can throw in there that may not see standpoint as being significant, but could help identify risk. So it has multiple kind of advantages to these techniques, but it allows you to have more things at your disposal for identifying those that are at risk, allows you to come up with this risk score, like I said, instead of just high risk or not high risk. And then what we look at in those cases is concentration of risk, which is really this tiered sensitivity value. It's the proportion of observed suicides that occur within a given tier of risk based on modeling, and everyone gets a predictive score and ranks them. Again, I'm not getting into the methods in this presentation. But you see is that there have been some examples recently of successfully using this approach. This is just a recent paper using Army STARS, predict suicides after psychiatric hospitalization in U.S. Army soldiers. So a high-risk group, no doubt, there's psychiatric hospitalization. We know these individuals are at increased risk for suicide. You can see on this figure that given learning techniques they used and these predictive scores they were able to generate using numerous risk predictive variables, they could get a pretty high concentration of risk within the top ventile of predicted risk based on the score that came out of that modeling technique. Over 50% of the suicides which followed hospitalization occurred among individuals with the top ventile of predicted risk scores. This helps us to again, focus on sensitivity or concentration of risk, allows us to improve screening measures. Doesn't solve the problem by any means of rare events, but an analytic approach to help us find that needle in the haystack. Challenge that we'll talk about today is really choosing an optimal study design. I'm not sure if this is really a challenge. Basically, just trying to keep the format of this relatively uniform, but this is a kind of a, I don't have to spend much time on this one at all, especially since we're running short on time, but essentially an optimal study design is, of course, one that answers your question of interest, but it also needs to be feasible, and part of that feasibility is understanding the limitations of working with rare event and what study designs will work best. No time on cross-sectional, really not something we do when we're looking at mortality or suicide as the outcome. It's where exposure and outcome measured simultaneously. And they're helpful. We do it when we're using, and I'll get into this later, when we're looking at non-fatal self-directed violence. There are some advantages of that. There's large national data sets that are cross-sectional, such as behavioral risk factor surveillance system. They have a lot of information on a lot of variables that are collected, a large number of people. Can then be rather, inexpensive and a bit to researchers. You can't assess temporal relationships and I don't do this with mortality, but when you have a rare event in there, you're still going to have any analytic complications that come along with having a rare event. Cohort studies, often talked about as longitudinal. This would be a prospective cohort study. They can also be retrospective. These are often of great interest because we want to understand temporality between risk factors, exposure, over time. We do this a lot with in the VA because we have administrative data and we can do retrospective studies. And we don't have to, classic cohort study would be very difficult with rare outcome, especially if you're waiting for your final endpoint of suicide, because you would start with a cohort of individuals who do not have the exposure and follow them forward in time for the outcome. But of course, when your outcome is rare, you're going to have to follow a very large number of individuals in order to have enough outcomes to do a meaningful analysis. So that's really the limitation of a cohort study when you have a rare outcome. We're able to use second data, such as administrative health data, and have a very large data set, such as the national VA data. It is certainly possible to do this. Not always available, of course, inside. And doing these important prospective cohort studies can be very challenging. And so this, I think we'll have a couple more slides on this. This talks a little bit about study designs which can help to overcome the rare outcome. And that is that one value of an outcome is rare, resource can be saved by randomly selecting within categories of the outcome. The way we do this is with, your classic case control design or your case cohort design. What you're doing in each of these cases is changing the ratio of the cases to control. So from an analytic standpoint, you don't have a rare outcome anymore because you're using either cases and controls or maybe not as balanced, but much higher than you would have observed in a cohort study. Essentially, you still have to deal with this from an analytic standpoint, though. You have to adjust that you aren't using, level or randomly selected data, so you've skewed the case control. You can't get rates out of that, of course, things like that. There's limitations, but it helps you from an analytic standpoint so that you're not dealing with problems. Another way to deal with this is from a study point is to not focus on suicide. Now, this is interesting kind of field talk about the use of secondary or intermediate outcomes, because from an endpoint, secondary or intermediate outcomes are anything other than the final outcome of interest that's related to or on the causal pathway of the outcome. I'll talk about this in reference to clinical trials, not necessarily for suicide, but I'm saying so you might be looking for biological markers instead of the endpoint of interest, and that's the secondary or intermediate outcome. Is that we reduce follow-up time, we can increase study power when the outcome is rare. But when secondary outcomes, and again, I'm just talking about general right now, not suicide, you may have an incomplete picture of treatment benefits or risks or a biased estimate of your relationship of interest if you're truly interested in that, primary endpoint. Now, if our primary endpoint in suicide is we want to prevent suicide death, visualize that anything other than death is an immediate or secondary outcome. Slightly saying that because as we can see in suicide, death is only the tip of the iceberg, something that's very well recognized. We have about 1 million individuals who attempt suicide each year, greater than 8 million reporting suicidal ideation, and those events alone are important and need to be prevented and need to be treated. So you don't need to study non-fatal self-directed violence in context that the things we may get when we study fatal self-directed violence as our outcome of interest may not be the same as what we would see if we were studying suicide. From a standpoint, these non-fatal events are certainly on the causal pathway and very important risk factors for suicide. And as I said, they're also unique outcomes, important unique outcomes that need to be prevented. I said we have to keep the context because risk factors and relationships for non-fatal self-directed violence and suicide can vary. Kind of goes back to the classic idea that these secondary or intermediate outcomes may provide a picture that's different than what we would see if we use the true endpoint of interest. Really classic examples that suicide rates are more than 3 times, nearly 4 times higher among men than women, but suicide attempts is considered more common among women. So right there, a concrete example of the fact that there's different risk factors, likely different problems. Another example that's a little bit more specific that I can talk a bit more about from personal experience is that psychological autopsy studies suggest about 90% of suicide decedents have a history of non-fatal attempts. Sorry, that's missing word attempts there. You may say, okay, well, studying, suicide, preventing suicide attempts, I don't have enough in my question of interest to look at suicides, but I'm going to focus on preventing repeat attempts as my outcome of interest. And clearly that's very related to suicide mortality. But one example to say again that this isn't always the case is just something that we're starting to see in veterans. This may not be the case for all subpopulations. We won't get into, again, too much detail here, but this I recently presented at APHA. The script is in prep, so this is just kind of a snippet of what we saw and what was presented at APHA. But we've looked for veterans. We've looked at differences between veterans who die by suicide who do and do not experience at least a documented suicide attempt in the year prior to death, and there's considerable differences in key risk factors. There's the gender one, which we just discussed, the likely related, but if I can just quickly draw your attention towards the bottom, if we looked at mental health and substance abuse diagnoses in the year prior to death, the prevalence of those diagnoses is much higher among suicide students who had a prior attempt than those who did not. And so we're using attempt as our outcome of interest. We are potentially missing a large population in veterans. I guess it's not shown in this figure. In veterans, we only found that 3% of those who died by suicide had prior to death, and so it's really a large group we could be missing who die by suicide and don't experience an attempt. And if we focus on attempt as the outcome of interest, relationships that we observe will certainly be important and useful, but we need to interpret our results in the context, which is different than if we were using the true outcome, not necessarily true outcome, but the final outcome of suicide death. So again, terms or approaches when it comes to choosing an optimal study design, I've just been saying this all along, and for this challenge example, it's really one of making a choice regarding what's the best design to answer your study questions, what resources you have available, and those resources could be time, money, data, access. I think I mentioned before that designs that select on the outcomes, such as the case control study and the case cohort study, they require statistical corrections often, not all the time, but depending on what your analysis is, such as weighting, so that you can accurately estimate risk or risk ratios. So you can kind of fix that rarity problem on one end, but then you have to adjust for the fact that design was not a random sample, essentially, on the analytic end, which is definitely very feasible and possible. And just to kind of summarize it, is that the suicide are important study, and they can help us understand suicide risk, but again, interpretation is very more present results. Okay, taking my time here. Determining the appropriate analytic methods. I think the last couple of points I have to make are very broad, so I should hopefully do it in just under 5 minutes. Essentially, how rare or common an outcome is, it has to be considered when you're choosing your statistical methods for a study. Logistic regression is one of our go-to methods for understanding risk relationships. It's used to calculate an odds ratio, used in many, many studies to estimate relative risk. With regression, actually can result in biased estimates. Outcome is too rare, and actually when it's too common as well. Logistic regression essentially has limitations over the frequency of an outcome. This is because of small sample bias, at least when you're talking about rare outcomes. It's really more of a problem with a small number of cases, like I kind of explained in the beginning, not as much a problem of the rate or risk. It really just has to do with how many cases of the outcome that you have to work with. And without getting into the statistical end of this too far, what is used when we're using logistic regression in SAS or any other program is maximum likelihood estimation, and that produces a biased estimate of beta, and that's a biased estimate of your odds ratio. When you both and basically rare events are a small number of cases. And that bias is that the probability of an event is often underestimated. And getting into the methods, but essentially our solutions for this when we're determining the appropriate analytic method is to really just consider not what's always used or what we see published on most, logistic regression, but to think about this, to talk with the statisticians we're working on, and to consider alternatives that may improve the accuracy of the estimates we're looking to make, whether it be an odds ratio or some other estimate. And with this, I'm just going to point out that alternatives do exist to help us cope with this rare event problem. There's exact logistic regression, there's penalized likelihood logistic regression, and there's others as well. So to get into the statistical end, but just to say that we need to consider when we have a small number of events in our study, whether kind of methods or go-to methods are actually appropriate, or whether we need to consult with a statistician and think a bit more about it. Related note is what I have listed here is challenge 5, covariate adjustment. There are a multitude of recognized risk factors for suicide across the social and ecological model. This is just the figure from the 2012 National for Suicide Prevention. Just to point out that in any given study, we are going to want to consider multiple variables. Adjustment when we're doing multivariate modeling. And just the type of modeling is important when we have rare events. There's also the issue of how much we can adjust for in terms of covariate. And without getting into the statistics in too much detail, there's often the rule of thumb that I mentioned way back in the beginning of this is that suggested for logistic and Cox proportional hazards modeling, two of the most common models used. There should be a minimum of 10 outcomes or events per particular variable. Our solution is that may make it seem like we can't adjust for important covariates if we don't have a large study working to find enough outcomes. There are actually studies that have been done that show it. You could potentially relax that 10-event rule of thumb and still have estimates. And I'll show you a slide in a minute with a reference to check out. And then another method, which is a very useful one, I wanted to use it as a transition for, I think it's next month's talk. Todd Wagner is going to be talking about propensity score methods and multiple uses for propensity scores. One of those is that we can use this method for covariate adjustment, and be able to learn more about that in the seminar. But very broadly here, what it allows us to do is to use logistic regression to generate a score combining multiple covariates of interest that our study participants we have information on. And thus, instead of putting in multiple covariates into our model that may not have enough outcomes to essentially hold all those covariates, and you'd run into convergence problems or you run into power problems, you can gain one covariate, the propensity score, in place of multiple covariates. And so from a statistical standpoint, you're able to do a fair amount of adjustment for variables we know we need to adjust for. From a statistical standpoint, you don't run into as many challenges. And again, details of that you can get from, I believe, the next focused AAS seminar. And just interesting, when I was reading about this a bit, relaxing the rule of 10 there is this publication in the American Journal of Epidemiology, which suggests that it's really not until under 5 often that you have major issues in terms of the confidence interval, and estimate. So you actually can often adjust for more than is typically recognized. But this would be a good article to read a bit if you were interested in that option. So I know we're over, and I will stop now.
Thank you. So thank you everyone for attending. If there's any questions, you can kind of put them in the chat, or you get email, so I can always forward it on to Claire. If you need community education credits, you can also email me as well. That's my email, so it came with the webinar link. So yeah, thank you everyone, and thank you, Claire.
You're welcome.